So when you look at populations, they're talking about continuous. We don't. You can model with, I guess, compound interest kind of thing. Like you could calculate a population increase every month or something, but we just use continuous. Things will fluctuate. So as you look at this, what is the R value here? What's 0.0367? If they put the decimal of 0.0367 in there, what is it? .66%, 3 2/3%. That's how fast this population is growing. So then a lot of times what they do is, we don't always go back to year 0. They want to model it from 1980 to 2008. Now typically we don't model populations over 28 years because things happen, right? The correctors, there are natural disasters, there are plagues, there are things that happen with populations that, well, not now, but I'm saying over time, right? So things can happen where the population changes. So T sub 0 is 1980. Use this model to predict the population 28 or 2008. So how many years is that? From 1980 to 2008 is how many years? 28. So what we're going to do is take our population for 28 years is equal to 32,000 e to the 0.0367 times 28. What do you get? $89,419. Okay. Predicted population. So people actually are, that's why we do the census. And they only, we do the census every 10 years because even after 10 years, it starts to, things change. Like right now in Minnesota, even when you look at outstate versus metro area, the metro is growing faster, right? People are coming from the rural areas into the population centers. All this stuff happens, and they need to correct their predictions. But they use predictions to, how much money are we sending here, here, and here? How many delegates do you get? How many of this, all that? Is that the last problem? Oh, one more? Oh, half-life problems. So another use exponentials is to talk about half-life problems. Carbon-14 is constantly being emitted. So they take the size of things, like when they find a body, frozen in the ice for thousands of years, they can estimate the size of it, and they estimate how much carbon-14 would have been in it when it was alive, and then how much is left. They can use, a Geiger counter or something, right, to figure out how much is there or something. I don't know.
What would they care about that?
What?
What would they care about that?
Well, how much is left now? They know its half-life is 5,730 years. So if they estimate, like, let's say 10 grams are supposed to be in my body, and they find me 5,730 years from now, and they estimate that there's 50% left, they know I've been frozen in the ice for 5,730 years. That's what happened. The carbon-14 stays around for so long. That's why it's a good thing to use to try and predict how long I've been frozen in ice. Yeah, so that's the little formula they give us. They're saying first, determine the initial quantity when t equals 0. So Q equals 10 times, most of you probably type in 0.5 t. So we put 0 up there divided by 5,730. Now, half-life problems change from time to time, but all we're doing is plugging in 0 for the t. What is 0 divided by 5,730? 0. What's 0.5 to the 0 power? 1, which is 10. So right away, before I got frozen in the ice, I should have had 10 grams in my body. So at t equals 0, we have 10 grams. Part B, 2,000 years. Now you have to kind of understand, some of these answers get really weird. But you should be able to look at that problem and is 2,000 a half-life? No. Is it half of the half-life? No. So when you think about it, if I'm going to lose half of the value in 5,730 years, I would lose five of these grams, right? I'm not even going to lose half of that right now. Correct?
Yeah.
So my answer that I come up with better be somewhere between 5 and 10.
75.
What is it?
7.85.
7.85. You know, so is it more than a third?
Yes.
So in other words, I'm going to lose somewhere between a third of the 10 and half of the 10. So that's, if you're coming up with answers that are, you know, 0.0009, the red flashing light should turn on and say, whoa, something went wrong in my calculator. Try to think through the problem. So, 1,000, 2,000, 3,000, 4,000, 5,000 years. We were right here, and I'm at 7.85, which would be about right there. Maybe a little higher. Right there. Something like that. Because now we're going to go up to 10,000 years. How many half-lives have we gone through at 10,000 years? One full half-life. Have we got to the second? So in your head, you should understand in the first one, I'm going to drop to 5 grams. In the second one, I drop to 2.5. So what two numbers should my answer be between? 5 and 2.5, right? Because I haven't got to the second half-life yet. What do you get? So 10 is what? 2.8? 2.98, so about right there. So the idea is our graph is coming down. And then when does it reach 0? Never, right? We'll never touch 0. Is that my last problem?
Yeah.